Hello everyone, this is Dr. Zach. Today we are going to discuss tail end behavior and the asymptotes of a function. Let's get started. For your lesson preview, you were asked to use limits to describe what's going on with your tail end behavior. The right tail is on the right side of the graph, the left tail is on the left side of the graph. Your right tail, you use the limit as your x goes to infinity, which means the right side of your f of x. Now, since the tail is heading upward, it's going to positive infinity. For your limit as x approaches negative infinity, your answer is negative infinity. For question B, you're going to use limits to describe the vertical asymptotes for this function g of x. Draw in the vertical asymptote. You can see that there's probably a vertical asymptote at x equals -2. So you would write the limit as x approaches -2 from the left of your g of x, and on the left side of g of x, notice that the asymptote is heading downward. So if it's heading downward, that's going to be equal to negative infinity. And the limit as x approaches -2 from the right of g of x is going to be positive infinity because it is heading upward on the right side. For your vertical asymptotes, you always have your answer heading towards positive or negative infinity. Now, as you look at the oblique asymptote, draw it in. Your oblique asymptote is describing what's happening as your end behavior again. So you have your right end behavior, you have your left end behavior, and for an oblique asymptote, that behavior is once again going towards positive or negative infinity. So to sum it up, your vertical asymptotes, your answers will always be plus or minus infinity. You recognize a vertical asymptote because you have a non-removable discontinuity, or you're dividing by some sort of zero in your denominator. Now you can use a sign chart in order to figure out if it's positive or negative infinity. And as f of x is approaching infinity, from the left to right, the line x equals c is going to be that vertical asymptote. For your tail end behavior, your answers can go to positive or negative infinity, or they could possibly head towards some sort of number. Polynomials generally go to positive or negative infinity. Rationals can have both horizontal or oblique asymptotes, and those answers would then go towards some sort of number or L, and the oblique asymptote will go to positive or negative infinity. Your trigonometric functions, the tail end behavior often oscillates, so those do not have answers when we talk about limits. So a horizontal asymptote is going to approach L, and this creates a horizontal line at y equals L. For an oblique or slant asymptote, this will end up with a positive or negative infinity as your tail end behavior. And we will use polynomial long division in order to describe the remainder and find our asymptotes. So for question 1, we're going to decide if it actually has a vertical asymptote. So we look at the denominator of each question, figure out if they have zeros. So for example, number 1 has a vertical asymptote at x equals -1. Question number 2 has 2 vertical asymptotes. See if you can find them. Question number 3 has multiple vertical asymptotes because we want to know where the cotangent of x has a denominator equal to 0, and the denominator, of course, is going to be your sine of x. So sine of x equals 0 when x is equal to pi k, where k is 0, plus or minus 1, plus or minus 2, etc. So make certain you write it so that you show the infinite number of answers. Now, for question number 4, be very careful. If you were to factor this problem, you're going to end up with x plus 4 times x minus 2 over your x minus 2 times x plus 2. you can see that there's a removable discontinuity at x equals 2. That's a hole. That's not a vertical asymptote, so you want to be very careful when you run into such a problem. So this one has a vertical asymptote at x equals -2. So as we think about horizontal asymptotes, we're going to find the limit as x goes to positive or negative infinity. So for question number 5, if we take the limit as x goes to positive infinity, that's asking about the right tail, for the sine of x over x. You have an oscillating function for sine of x in the numerator, and you're dividing by infinity. Now, the sine of x is slower than x as we head towards infinity. So although it's oscillating, x is pulling it and the answer becomes 0. We cannot use L'Hopital's rule for this problem because it's not 0 over 0 or infinity over infinity, your indeterminate form. So the horizontal asymptote in this problem is y equals 0. For question number 6, you want to think about the exponents. Here's x squared and x squared in both the numerator and your denominator. If you take the limit as your x goes to positive infinity, or even x goes to negative infinity, what's going to happen? You're going to drop your lower order terms and be left with 4x squared over 2x squared. The x squareds will cancel out and you're left with 2. So this has a horizontal asymptote at y equals 2. Similarly, if you took the limit as x goes to negative infinity, you still get your 4x squared over 2x squared, which will take us to positive 2. So in this problem, you do have horizontal asymptote at y equals 2. You are not guaranteed to have that horizontal asymptote for both positive and negative infinity. So let's take a look at this next question. We have the limit as your x goes to positive infinity of 4x cubed, dropping those lower order terms, 2x squared, and you get 2x. Oops, don't lose that limit notation. So we get the limit as x approaches infinity of 2x. Now, because this is a rational function, we know that there's going to be an oblique asymptote that our function will follow. So you're going to have to find it. Now, for me, I prefer polynomial long division, but if you prefer synthetic division, please do that. I'm going to show polynomial long division whenever I solve one of these problems for you, though. So let's get started with that idea. So you ask yourself, what times your 2x squared gives you 4x to the third? And that's going to be 2x. Multiply, you get 4x cubed plus your 2x. Next, we subtract. When you subtract, change your signs. You're left with negative 2x plus 1. And you ask yourself, what times 2x squared is negative 2x? And that's when you get into fractional exponents, which we don't want. So f of x can be rewritten as 2x plus your negative 2x plus 1 over 2x squared plus 1. So you have an oblique asymptote at y equals 2x. This other part of the problem will actually go to 0 and won't count, but the oblique asymptote that your function will follow is the line y equals 2x. Now, question number 8. If you take the limit as your x goes to positive infinity for f of x, you will end up with a couple of different things happening. You drop your lower order terms, which leaves you with the limit as x goes to positive infinity, 8x over the square root of 2x squared. Now, we know that the square root of x squared is actually equal to the absolute value of x. So we get x goes to positive infinity, 8x over root 2, absolute value of x. And we also know that this answer is positive or negative 1, depending on what your x is doing. So as x approaches positive infinity, your answer is going to be 8 over the square root of 2. But if you take the limit as x goes to negative infinity for f of x, your answer becomes negative 8 over the square root of 2. So keep an eye on your square roots. Make certain that you acknowledge there could be two answers. So we're going to determine the oblique asymptotes for both of these functions. First, you should ask yourself, how do you recognize it has an oblique asymptote? If you look at the end behavior, the limit as x goes to infinity, your answer for f of x is going to be positive infinity or negative infinity, depending on which way you're approaching. So that is your clue, since it's a rational heading towards infinity, that you have an oblique asymptote. Now, if we do polynomial long division, x minus 5 divides into our 2x cubed plus our 0x squared minus 8x minus 1. Figure out what times x is 2x cubed. So that's going to be 2x squared. Multiply, we get 2x cubed minus 10x squared. Change your signs. When you change your signs, you end up with 10x squared minus 8x. So now we're going to multiply by a positive 10x, and when we do, we end up with our positive 10x squared minus 50x. Change your signs again, and you end up with a 42x. Yes, that's annoying. Bring down your minus 1. Multiply by your 42. So we've got plus 42 now. That gives us 42x minus our 210. Change your signs and subtract. That'll give us 209. So our problem can be rewritten as the nice little expression 2x squared plus 10x plus 42 plus 209 over x minus 5. So your oblique asymptote is the part of the problem that does not go away. That's y equals 2x squared plus 10x plus 42. Now you're asking yourself, what kind of an oblique asymptote is that? If you were to graph the equation y equals 2x squared plus 10x plus 42, it is a parabola. And your function is going to follow that parabola either above or below, and it's going to have a vertical asymptote at x equals 5. So it's going to be a very interesting problem once we're ready for it. All right, try example 2. Try this example. Make certain that you're able to do polynomial long division to find your oblique asymptote. All right, so for example 2, we're looking for the asymptotes, and then we're going to sketch our graph. So when we look for the asymptotes, we want to think about where we have the zeros in your denominator. So the vertical asymptote for this one, you can see that we're going to have x equals 3 and x equals negative 3 as those vertical asymptotes. Make a statement. Then we're going to do an analysis. The limit as x approaches 3 from the left of our function f of x. The limit as x approaches 3 from the right of our function f of x, because we want to know if we go up or down the asymptotes. For x equals 3, negative 3, we're going to do something similar and take the limit as x approaches negative 3 from the left of f of x. And we also want the limit as x approaches negative 3 from the right of f of x. So we already know the answers are infinity. The question is, are they positive infinity or negative infinity? So think about a number slightly to the left of 3. Let's say 2.9. If you were to substitute 2.9 in for f of x, 2.9 will give you a positive divided by a negative. And a positive divided by a negative is going to be negative infinity. If we substitute a number from the right, let's say 3.1, we will get a positive divided by a positive, so that tail is positive infinity. Now, to the left of negative 3, so let's look at negative 3.2. When you substitute in, you get a negative over a positive. So it's going to go downward for negative infinity. And then if we look at negative 3 from the right, let's say negative 2.9, we're going to get a negative over a negative, which of course is a positive. So we have done a sign analysis. We know that our asymptotes, we're going to go down the asymptote, we're going to go up the asymptote. As we're on the left side of negative 3, we're going to go down the asymptote. And then for the right side of negative 3, we're going to go up the asymptote. Next, we're going to think about our horizontal asymptotes. So for your horizontal asymptote, we know we're going to take the limit as x approaches infinity for f of x. Now, fortunately, the 2 over 9 will cancel, and we're left with x over x squared, or essentially the limit as x goes to infinity of 1 over x, and that is 0. So we have a horizontal asymptote at x equals 0. All right, so the next thing, in order to get a good graph, we want the x-intercepts, the y-intercepts, we want to talk about domain restrictions and end behavior. So the x-intercepts, when we think about that we're going to let your y equal 0, and when y equals 0, we get x equals negative 2. When we look for the y-intercepts, we're going to let x equal 0, and we have y equals negative 2 over 9. The domain and some restrictions. So for the domain, you should write that the domain is going to be from negative infinity to negative 3, don't include it, union, negative 3 to 3, don't include 3, union, 3 to positive infinity. And when we talk about your end behavior, that's going to be your horizontal asymptotes. Function shifts and transformations, we're going to get a lot of information just from what we have now. First, we're going to draw in our vertical asymptotes, and those vertical asymptotes occurred at negative 3 and 3. So use dashed lines to draw those in. These are like the bones of your graph, so it's good to have nice bones before you begin. Afterwards, we're going to draw the horizontal asymptote at 0. Now, since it's on the axis, I'm going to draw those slightly slanted. Now it's time to take all of our information and graph the function. We're going to begin with our vertical asymptotes. On the left side of negative 3, the vertical asymptote is heading downward. On the right side of negative 3, according to our analysis, the asymptote is heading upward. Then let's look at 3 from the left. Our analysis tells us that the asymptote heads downward. On the right side of 3, the vertical asymptote heads upward. For our horizontal asymptotes, you want to use a general idea of where the vertical asymptotes are located. We know that we're going to approach 0. So the question becomes, do we want to be above or below the y equals 0? So take a notice that the vertical asymptote is below the axis, and we're going to follow the same idea in order to draw the horizontal asymptote to connect them. There we go. The other horizontal asymptote, still following 0, and once again you want to think about, do I want to be above or below the axis? And since we have our vertical asymptote above the x-axis, we're going to do the same thing and draw in the rest of our graph above the axis. Next, we want to think about our x-intercepts. The x-intercepts are going to be 0, negative 2 and 0, so plot that point. Then we have 0, negative 2/9, plot that point. We want to then think about the domain restrictions, and our domain restrictions are the vertical asymptotes. We're going to put everything together and graph as best we can and connect all of our pieces. So now we have the asymptotes that help determine our sketch. And as you can see, they are the bones. We might not have it perfectly drawn, but at least we have a really good sense of what's happening. For example 3, we're also going to determine our asymptotes and sketch the graph. To sketch the graph, we should find our x-intercepts, our y-intercepts, the domain range restrictions, and some end behavior. So let's take a close look at what's going on here. We have f of x is equal to this lovely function. We're going to let y equal 0, and when y equals 0, we get 6x cubed plus 5 is equal to 0. Now, you might be wondering if you're going to use a calculator to solve these problems. The answer to that is no. You're expected to just solve them without your calculator. So now, with that in mind, let's take this and have x cubed equals your negative 5 over 6. And then we want the cubed root of negative 5 over 6. So x is equal to some sort of negative value. And remember that negative value is smaller than 1, so that answer is going to be smaller than 1. You are not going to be able to graph with precision, and that's okay. Now, for the next part, if we let x equal 0, we will end up with our y equals 5. So we now have 0, 5, and negative 5 over 6 to the 1/3, comma 0 as interesting points. The domain of this problem is actually all real numbers. As you look at your denominator, 3x squared plus 1 is never equal to 0, so we have no vertical asymptotes, and you should make that statement so that the grader understands that you have thought about it. We next want to think about your horizontal asymptotes. So for the horizontal asymptotes, if we take the limit as x goes to infinity for our 6x cubed plus 5 over 3x squared plus 1, the answer is going to infinity. So you know it, we have some sort of slant asymptote, and we need to find it. And to find it, what are we going to do? You are right, we're going to do some long division. Take your 3x squared plus 1 and divide it into 6x cubed, leave some space, and a plus 5. And when you do your multiplication and division, you get your 2x is going to be 6x cubed plus 2x. This is subtraction, negative 2x plus 5. You now know that your function could be rewritten as 2x plus negative 2x plus 5 over 3x squared plus 1. So you have an oblique asymptote or slant asymptote at y equals. Now it's time to put everything together to build our graph. We're going to graph first the asymptote because it is the bones of the graph. So we will graph our y equals 2x. Be as precise as you possibly can be. Imprecision is going to occur when we plot some of our points, such as negative square root of 5, 6. But things like y equals 2x, we can control. Plot the 2 points that we know. We have 0, 5. Now, negative third root of 5, 6 is smaller than 1. I'm just going to put a dot in. When we follow the asymptotes, we will follow along our asymptote on the same side as the points that we've built. So connect the arrows through your dots. There is curvature in this graph. We'll get more clarity on the curvature when we talk about concavity. And as we step back and look at that graph, we have our function f of x. Let's take a look at example 4. Once again, we need our x-intercepts and y-intercepts. When we let x equal 0, you can see that there is a domain restriction. So we will not have any points on our y-axis. So next, let's figure out what happens when we let y equal 0 or h of x equals 0. 0 equals your x cubed plus 1, which of course tells us that x equals negative 1. And we have our point, negative 1, comma, 0, and no y-intercept. After that, we think about the domain. We have the good information here that for our domain, the domain is going from negative infinity to negative 1, union 1 to negative 1 to positive infinity. So we're skipping negative 1. We will have a vertical asymptote at x equals negative 1. With that, you need to write out the limit as x approaches -1 from the left of our function h of x, and we want the limit as x approaches -1 from the right of h of x. As we approach -1, we know the answer has to be some sort of infinity. The question is it positive infinity or negative infinity? Once again, do some sort of analysis. If I'm on the left side of -1, you might think of -1.1 when you do some substitution. And when we substitute in -1.1, we will have a negative over a negative, which of course means we have positive infinity. As you're thinking of -1 to the right, you might be thinking of -0.9. And if you were to substitute -0.9 in, you will have a positive over a negative when you substitute into h of x. So that tells us we have negative infinity. So the left side is going up the asymptote, and the right side is heading down the asymptote. Let's think about our horizontal asymptotes. As we think about the limit as x goes to infinity, whether it's positive or negative infinity, you are getting, oh, look at that, positive infinity of h of x gives me positive infinity, and the limit as x goes to negative infinity of h of x will give me also a positive infinity. So they're both heading upward. What that tells us is we need to do a little bit of division. And when you do your division, you can even do monomial division for this one because it's just a nice little monomial. You don't have to do long division. We end up with an oblique asymptote is equal to x squared. The 1 over x will go to 0 as we go to infinity. So our oblique asymptote is y equals x squared. So that's going to be a fun graph for us to put all together. Begin, of course, drawing your oblique asymptote, y equals x squared. Draw it carefully. You want to have this as best you can. So when you put in your values, there we go. And when we have 3, that'll give us 9. All right, I've got my oblique asymptote drawn in of y equals x squared. This one also has a vertical asymptote at 0. So let's put in our 0, drawing it slightly slanted along that line. There we go. So we have the bones of our graph. We want to put it all together. Plot your 2 points. Our first point was -1, 0. That's going to be a very useful point. Notice that we are on the left side of the graph. So when we head up the asymptote and down the vertical asymptote, we're going to be on the furthest left side of the graph. Now, we also know to the right of 0, we were heading up the vertical asymptote. So we're going to draw in a nice little arrow to indicate that we were heading upwards. And since we have this arrow heading upward inside our little region, we're going to draw the other arrow, which is supposed to go upward, inside this pocket. Sketch the graph now using the information you have, and you have a pretty good representation of your graph. Now my graph is very wiggly. Try to draw yours so that it is less wiggly, and we will be set. Your takeaway from these examples will be that the asymptotes provide bones for the graph. You use limits to figure out whether or not you are heading up the asymptotes, down the asymptotes, and which side of the graph you are following. Use your asymptotes to get excellent pictures. Example 5 has a fabulous little square root in it. This is going to make our problem so much more interesting. Talking about your x-intercepts first. So the x-intercepts occur when your y is equal to 0. When 0 equals the square root of 9x squared minus 2. Square both sides, solve it, you come up with x is equal to plus or minus the square root of 2 over 9. Now your y-intercepts occur when you let your x equal 0, which leaves us with a negative under a square root. So we have no y-intercept in this problem. Next, we'll discuss the domain. Your domain has two features to think about. You have to be positive under your square root, so 9x squared minus 2 is greater than or equal to 0, but you may also not have a 0 in your denominator, and we will have a 0 at x equals negative 1/2. Therefore, a vertical asymptote is going to occur at x equals negative 1/2. We'll do that analysis in a moment. Solving this equation or inequality, we get x squared is greater than or equal to 2 over 9. And of course, when we find a square root, we know that x is greater than or equal to square root of 2 over 9, and x, which one is it? It's an or. X is less than or equal to our negative root 2 over 9. When we put the domain all together, we end up with your domain. So our domain is traveling from negative infinity to negative 1/2, not including the 1/2 union, negative 1/2 to negative square root of 2 over 9. We're going to skip part of the graph between negative root 2 over 9 and root 2 over 9 and rejoin the graph from root 2 over 9 all the way to positive infinity. So the domain makes this a very interesting problem. So now let's look at our vertical asymptotes. The vertical asymptote, we're thinking about the limit as x approaches negative 1/2 from the left of our function f of x. And if I'm on the left of our function f of x, we know that the answer has to go to infinity or negative infinity. On the left side, I might be thinking about negative 0.6. And when I do my substitution, the numerator is positive and the denominator is going to be negative. So I'm heading towards negative infinity. Next, we'll think about the limit as x approaches negative 1/2 from the right-hand side. From the right-hand side, I might be thinking about negative 0.4. The numerator is positive and your denominator is going to be negative. So my graph is heading towards negative infinity as I approach that asymptote. What about your horizontal asymptotes? So for the horizontal asymptotes, let's think about the limit as x goes to positive infinity for the square root 9x squared minus 2 over 2x. So the 2 cancels out. You're left with the square root of 9x squared. And as we do an analysis, this is the limit as x goes to positive infinity, 3 absolute value of x over 2 times x. So as I'm going to positive infinity, the answer is 3 over 2. But if I take the limit as x goes to negative infinity, the answer is negative 3 over 2 when I think about f of x. So I have two different horizontal asymptotes. So this, see, my friends, is a very fun function. All right, draw the asymptotes first. We will think about 3 over 2. So 3 over 2 will be right here. Negative 3 over 2 is what we're going to graph next. And make certain that when you do your analysis, you write that this is a function y equals 3 over 2 and y equals negative 3 over 2 for our asymptotes. We also had, as you'll recall, x is negative 1/2. So we're going to draw that asymptote in. So we have all the asymptotes in place. Now let's plot the points we have. We were given root 2 over 9, which is a slightly smaller number than 1. We also have negative root 2 over 9, so plot those 2 points. Follow the asymptotes. On the left side of negative 1/2, we were going down the asymptote. On the right side of negative 1/2, we were going up the asymptote. What about the horizontal asymptotes? We want to follow the general picture. When we go to positive infinity, we're going to be underneath the horizontal asymptote. And as we go to negative infinity, we're also going to be underneath the horizontal asymptote. Connect your pieces together. We have a nice curve on the left side of the graph. On the right side of the graph, we have a curve. And let's think about what's happening between -1/2 and -√2/9. We have some sort of line. It's not a straight line, but because we have such a small region, graph the best you can. Notice nothing is happening between the -√2/9 and +√2/9. That's great because our domain had a restriction that said place nothing between them. So our final graph is complete. This is our function f of x. Now it's time to practice some of these problems. Keep in mind that the asymptotes are the bones of your graph. You have an excellent day.